On January 12, 1920, a man who was 3 months away from dying picked up a pen in Kumbakonam, a small temple town in southern India, and wrote a letter to G.H. Hardy at Cambridge University. He apologized for the silence. He had been too sick to write, but he had something he needed to share before it was too late. He called them mock theta functions. He gave 17 examples. He described their properties in a few spare paragraphs, offered no proofs, and sent the letter off. The handwriting was shaky. The mathematics was not. 3 months later, he was dead. He was 32 years old, and nobody understood what he had written. That letter sat in various drawers and filing cabinets for decades. Mathematicians glanced at the mock theta functions, recognized they were unusual, published a few papers on individual examples, and moved on. Nobody had a framework for understanding what Ramanujan had actually found. The functions behaved like modular forms, which are among the most important and beautiful objects in all of mathematics. Functions with an extraordinary degree of internal symmetry. But Ramanujan's mock theta functions were not quite modular forms. They had a defect, a shadow. Something was off about their symmetry, and no one could say precisely what. G.N. Watson, who studied them longer than anyone, wrote in 1936 that Ramanujan's discovery of the mock theta functions makes it obvious that his skill and ingenuity did not desert him at the oncoming of his untimely end. But Watson could not explain what they were. He could only catalogue them, like a naturalist who has discovered a new species and cannot determine where it fits in the taxonomy of life. 82 years passed. In 2002, a Dutch PhD student named Sander Zwegers, working under Don Zagier at the Max Planck Institute in Bonn, finally cracked it. He showed that Ramanujan's mock theta functions are the holomorphic parts of harmonic, weak mass forms, which means if you add a specific non-holomorphic correction term, the symmetry completes itself. The shadow has a source. The defect has a meaning, and that meaning turned out to be physical. In 2012, Atish Dabolkar, Samir Murthy, and Zagier published a landmark paper showing that the generating functions counting the quantum microstates of certain black holes are not ordinary modular forms. They are mock modular forms, the very objects Ramanujan described in his deathbed letter. The defect in their symmetry, the shadow, encodes a physical phenomenon called wall crossing, where the number of stable black hole states jumps discontinuously as you cross certain boundaries in the space of parameters. When multi-centered black hole-bound states form or decay at walls of marginal stability, the count of single-centered, immortal black holes is not captured by a full modular form. It is captured by a mock modular form, by Ramanujan's shadow. A dying man in colonial India, who said a Hindu goddess placed equations on his tongue, had written down the mathematical objects that encode the internal quantum structure of black holes. Published, peer-reviewed, confirmed. A July 2025 review paper in the journal Entropy reaffirmed the result, and almost nobody outside of mathematics and theoretical physics has ever heard about it. This was not announced. There was no press conference, no headline in any major newspaper. The connection between Ramanujan's deathbed mathematics and the quantum behavior of the most extreme objects in the universe was established, verified, and then absorbed into the specialist literature without a ripple in public consciousness. You were never told this. the most extraordinary correspondence between pure mathematics and physical reality discovered in the 21st century, and it was treated as a technical result in a technical field. Think about what that means for a second. Not what it means about Ramanujan, what it means about mathematics, what it means about you and the universe you are sitting in right now. Because if mathematics were a human invention, a language we built to describe reality, the way you build a hammer to hit nails, then this could not happen. You do not accidentally build a hammer in 1920 that turns out to be the exact tool needed to fix a machine that will not be invented until 2012. You do not guess the answer to a question nobody has asked yet. You do not dream the solution to a problem that does not exist. But that is precisely what Ramanujan did, over and over. For his entire short life, he produced mathematical structures that had no known application, no physical motivation, no context in which they made sense. And decades later, those structures turned out to be exactly what physics required to describe the most extreme objects in the universe. The standard story about Ramanujan is that he was a tragic genius, born poor, self-taught, recognized too late, died too young. And that is all true. But it is the surface. The real story, the one that should unsettle you, is not about his life. It is about what his existence implies about the nature of reality itself. Because Ramanujan is the strongest single piece of evidence in the history of science that mathematical truth exists independently of human minds, that it was there before us, that it will be there after us, and that at least one person appears to have had direct access to it through a channel that nobody, not Hardy, not Littlewood, not the entire 20th century mathematical establishment, has ever been able to explain. And the most uncomfortable part of this story is not that nobody understood what he wrote. It is that we still do not fully understand it. The notebooks are not finished. Mathematicians are still proving him right. And some of what remains unproven may describe physics that does not exist yet as a science. His name was Srinivasa Ramanujan. He was born on December 22nd, 1887, in a road in the Madras Presidency of British India, at the home of his maternal grandparents. His family's permanent home was in Kumbakonam, a temple town about 160 kilometers to the east, where he grew up in a small traditional house on Sarangapani Sanidi Street. His father, Kupaswamy Srinivasa Iyengar, was a clerk in a cloth shop, earning about 20 rupees a month. His mother, Komalatamal, was a singer at the local Sarangapani temple, deeply religious, and the dominant intellectual influence in his early life. The family were Tamil Brahmin Iyengars, devout followers of the goddess Namagiri Taya, a form of Mahalakshmi worshipped at the Lakshmi Narasimha Swami temple in Namakkal. 3 of Ramanujan's siblings died in infancy. 2 younger brothers survived. By the time he was 11, he had exhausted the mathematical knowledge of 2 college students who boarded in his family's home. By 13, he had mastered SL, Loney's advanced trigonometry textbook, and was deriving sophisticated results on his own. At 15 or 16, around 1903, he obtained a library copy of a book that would detonate his life. George Shoebridge Carr's A Synopsis of Elementary Results in Pure and Applied Mathematics. It was a dry, Victorian compendium listing approximately 5,000 theorems without proofs, just results, one after another, statement, 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 without explanation, derivation, context, or motivation. Carr's book was not a work of genius. It was a study aid, already out of date when Ramanujan found it. But for a mind like his, it was a detonation. He took every one of those 5,000 results as a challenge, worked through them independently, reproduced them from scratch, and then kept going far beyond anything Carr had collected, producing original mathematics that no one in India and almost no one in England could evaluate. By 1904, at 17, he had independently developed the Bernoulli numbers and calculated the Euler-Mascheroni constant to 15 decimal places. Carr's terse, proof-free style profoundly shaped how Ramanujan presented his own work for the rest of his life. Result after result, dense, cryptic, and almost always without proof. This would later cause tremendous problems, but something else happened with Carr's book that is worth pausing on because it illuminates how differently Ramanujan's mind worked. Carr's synopsis was published in 1886. By the time Ramanujan found it, much of the mathematics it contained was already outdated. The book stopped before modern analysis had fully developed. Ramanujan did not know this. He had no way of knowing where the frontier of European mathematics stood. He was working in near total isolation, in a small town in southern India, without access to journals, without correspondence with other mathematicians, without a teacher who could tell him what was known and what was open. So he reinvented large portions of European mathematics on his own, from scratch, using methods nobody had ever seen. Some of what he produced matched known results. Some of it went far beyond, and some of it existed in a category that would confuse and frustrate Hardy for years. Results that were true, clearly true, but arrived at through reasoning that did not follow any established path. Stephen Wolfram, analyzing Ramanujan's notebooks decades later, observed that his method seemed almost computational, as if he were running experiments with numbers and infinite series, testing patterns and recording the results without caring whether anyone else could reconstruct the process. The notebooks read less like mathematical proofs and more like field notes from an expedition to a place nobody else could visit. By 1908, when he was 20, Ramanujan had filled the first of his 3 notebooks. He was working on problems in number theory, infinite series, continued fractions, and the properties of highly composite numbers, all while failing his college exams and sliding deeper into poverty. He married Janaki Ammal on July 14, 1909. She was 10 years old, which was not uncommon in that time and place. The marriage added financial pressure. He had a family to support and no degree, no job, and no prospects except his notebooks, which nobody he had met could evaluate. And here is where Ramanujan said something that Hardy, the great atheist of Cambridge mathematics, never knew what to do with. Ramanujan said, "An equation for me has no meaning unless it expresses a thought of God." He described his mathematical visions as experiences that arrived during sleep. There is an account passed through several retellings and debated among scholars in terms of its precise sourcing, in which he described blood-red screens on which a divine hand would write elliptic integrals that he would then record upon waking. He said of the goddess Namagiri in Tamil, "She wrote on my tongue." He said the goddess showed him scrolls of complex mathematics in his dreams, and that after waking, he would write down only a fraction of what had been revealed. Hardy dismissed the religious framing. He acknowledged the intuition was beyond explanation, but argued that divine attribution was overstated. Maybe he was right. But here is what Hardy could not dismiss, and what he never found an alternative explanation for. He rated mathematicians on a scale of 0 to 100 for pure natural talent. He gave himself 25. He gave his lifelong collaborator, Littlewood, 30. He gave David Hilbert, one of the 2 or 3 most important mathematicians of the early 20th century, 80. He gave Ramanujan 100. And when asked what his single greatest contribution to mathematics was, Hardy did not cite any of his own theorems, not the Hardy-Weinberg principle, not his work with Littlewood on the Riemann zeta function, not the circle method he co-developed with Ramanujan. He said, without hesitation, that his greatest contribution was the discovery of Ramanujan, finding him, opening that envelope, which raises a question Hardy never answered. If Ramanujan's talent was literally off Hardy's scale, operating at a level Hardy could not reach and could barely comprehend, and if Ramanujan himself said that talent came from somewhere outside him, from a goddess, from dreams, from a source he experienced as external, then what exactly is Hardy dismissing when he dismisses the religious explanation? He has no alternative explanation to offer. Nobody does. The question is not whether Namagiri is real in the way Ramanujan believed. The question is whether Ramanujan had access to mathematical truth through some channel that formal training does not provide, and that no model of human cognition can account for. And the evidence that he did is not anecdotal. It is not hagiography. It is written in the notebooks. It is published in the journals. It has been confirmed for over a century. But none of that happened smoothly, because the system that should have recognized Ramanujan nearly destroyed him instead. His obsession with mathematics wrecked his formal education. He won a scholarship to Government Arts College in Kumbakonam in 1904 and lost it the following year by failing every subject except mathematics. He enrolled at Pachayappa's College in Madras and failed the Fellow of Arts examination twice, in December 1906 and December 1907, passing mathematics with distinction while failing English, physiology, and Sanskrit. He never earned a university degree for nearly a decade. From about 1903 to 1912, he lived in extreme poverty, frequently on the edge of starvation, working out his mathematics on a slate because he could not afford paper. He would derive a result, copy the final answer into one of his notebooks, wipe the slate clean, and start again. The intermediate work, the steps, the reasoning was lost every time. This is one reason the notebooks contain almost no proofs. The medium itself erased them. In August of 1905, his mother placed a missing person notice in the Hindu newspaper because he had run away from home entirely. A small network of Indian supporters eventually recognized his talent and kept him alive. V. Ramaswamy Iyer, the founder of the Indian Mathematical Society, saw his notebooks and was stunned. R. Ramachandra Rao, a district collector in Nellore, was initially skeptical, but converted after Ramanujan spoke to him about elliptic integrals and hypergeometric series, and agreed to support him with 25 rupees a month from his own pocket. On March 1st, 1912, Ramanujan was hired as a Class 3, Grade 4 accounting clerk at the Madras Port Trust, earning £20 per year. One attraction of the job was that he could take home used wrapping paper to write his formulas on. This is where Ramanujan was working when he made his last attempt to reach a mathematician who could understand him. He had already written to two of the most prominent mathematicians in England. In late 1912, he sent his work to H.F. Baker, Fellow of the Royal Society and past President of the London Mathematical Society. Baker returned the papers without comment. He then wrote to E.W. Hobson, the Sadlerian professor of pure mathematics at Cambridge. Hobson also returned them without comment. M.J.M. Hill at University College London at least responded on November 12, 1912, but his assessment was patronizing. He said Ramanujan had a taste for mathematics and some ability, but that his papers were riddled with holes. Remember Baker and Hobson. They will reappear later in this story, and when they do, the irony will be severe. The third letter, dated January 16th, 1913, went to G. H. Hardy at Trinity College, Cambridge. It began, "Dear Sir, I beg to introduce myself to you as a clerk in the accounts department of the Port Trust Office at Madras, on a salary of only £20 per annum. I have had no university education, but I have undergone the ordinary school course. After leaving school, I have been employing the spare time at my disposal to work at mathematics." Attached were 9 pages containing approximately 120 theorems. No proofs. Ramanujan had chosen Hardy specifically after reading his 1910 book, Orders of Infinity. Hardy received the letter around January 31st, 1913. His first instinct was that it was a fraud, possibly an elaborate hoax. He recognized some formulas as known results. Others he had never seen anything like. He set the letter aside, went about his day, and returned to it that evening. He brought the pages to Littlewood's rooms. They spent hours going through the results one by one. The continued fractions on the final page defeated Hardy completely. He had never encountered anything remotely like them. And then he reached his verdict, the line that would echo through the history of mathematics. They must be true, because if they were not true, no one would have the imagination to invent them. Littlewood's assessment was equally electric. He told Hardy he believed Ramanujan was at least a Jacobi, invoking one of the titans of 19th century mathematics. Bertrand Russell, the philosopher, recorded the next day's atmosphere. He had found Hardy and Littlewood in a state of wild excitement because they believed they had discovered a second Newton, a Hindu clerk in Madras earning £20 a year. Now here is a misconception that needs correcting, because you have probably heard Ramanujan described as a kind of mathematical savant, a human calculator, someone who could multiply large numbers in his head or spot patterns in arithmetic. That description is wrong, and it is wrong in a way that obscures the real mystery. Ramanujan was not doing arithmetic tricks. He was producing deep structural mathematics, modular forms, partition theory, infinite series whose convergence properties professional mathematicians at the world's leading institutions could not replicate, verify, or in several cases, even understand. Hardy explicitly distinguished Ramanujan from calculating prodigies. The formulas in that 9-page letter included results on divergent series, hypergeometric series, continued fractions, and properties of the Riemann zeta function. Several were entirely new to mathematics. Several more were re-derivations of results that had taken European mathematicians years of effort to prove. And Ramanujan had produced all of it alone, without access to a university library, without knowledge of many of the tools that should have been prerequisites in the margins of his work as an accounting clerk. Consider just one example from the first letter. Ramanujan presented a continued fraction for a certain expression involving pi and the exponential function that, when Hardy and Littlewood finally analyzed it, turned out to imply deep properties of modular functions that were at the cutting edge of European research. Hardy later wrote that some of the results in the letter were already known to him. Some were new, but he could, with effort, see how they might be proved. But there was a third category, and it was this third class that convinced him Ramanujan was genuine. These were results Hardy could neither prove nor disprove. They were claims of such originality that Hardy had no framework for evaluating them. He could only recognize that they had the hallmark of truth, the internal consistency and aesthetic rightness that genuine mathematics possesses, while being unable to verify them by any known method. That experience of a leading mathematician at one of the world's great universities confronting results from an unknown clerk that he could not even approach is the core of the Ramanujan mystery. Hardy was not merely impressed. He was out of his depth. Hardy replied on February 8, 1913, requesting proofs. Ramanujan sent a second letter on February 27th with additional results. Hardy worked to bring him to Cambridge. The journey was not simple. Orthodox Brahmins believed crossing the ocean was a sin, the concept of Kalapani, or black waters. Leaving India meant loss of caste, spiritual contamination. Ramanujan initially refused. His mother was totally opposed. The impasse broke only when Kamala Tamil reported a vivid dream in which Ramanujan was surrounded by Europeans, and the goddess Namagiri commanded her to stop standing between her son and the fulfillment of his purpose. E. H. Neville, a Cambridge mathematician lecturing in Madras in early 1914, was enlisted by Hardy to handle the practical arrangements. The University of Madras provided a scholarship of £250 per year for 5 years. On March 17, 1914, Ramanujan sailed from Madras aboard the SS Navasa. He arrived in London on April 14th. He moved into rooms at Whewell's Court, Trinity College, a 5-minute walk from Hardy's rooms. The collaboration that followed was unlike anything Cambridge had seen. Hardy later described the dynamic in terms that reveal just how disorienting it was to work with Ramanujan. Hardy was a rigorous formalist, a mathematician who believed above all in proof. Ramanujan was the opposite. He arrived at results through a process that Hardy could not follow, and that Ramanujan himself could not always articulate. Hardy would ask how he knew a particular result was true. Ramanujan would sometimes offer a sketch of reasoning that Hardy could develop into a proof. Other times, he would simply say he knew. Hardy described the frustration and the wonder of this in equal measure. He said that working with Ramanujan was like working with someone who was receiving transmissions from a station Hardy could not tune into. The results kept arriving, and Hardy's job was to verify them, to find the proofs that Ramanujan did not need. Their most celebrated joint work, the paper on the partition function, published in 1918, introduced the circle method, one of the most effective techniques in analytic number theory, still actively used more than a century later. The partition function P of n counts the number of ways to write a positive integer, n, as a sum of positive integers without regard to order. It sounds simple. It is not. For small numbers, the partitions are easy to list. 4 can be partitioned in 5 ways. But the growth is explosive. The number of partitions of 100 is 190,569,292. The number of partitions of 200 is approximately 3.97 times 10 to the 12th. Before Hardy and Ramanujan, there was no practical method for computing these values for large n. Ramanujan had already discovered, on his own in India, that the partition function obeys remarkable congruences. The number of partitions of any number of the form 5k plus 4 is always divisible by 5. The number of partitions of any number of the form 7k plus 5 is always divisible by 7. And the number of partitions of any number of the form 11k plus 6 is always divisible by 11. These are not obvious. They are not things you would guess by looking at the numbers. They are deep structural properties that reveal hidden symmetries in the integers. Hardy called them among the most beautiful results in the theory of number. And for decades, they were treated as isolated curiosities. 3 remarkable congruences involving 3 specific primes, 5, 7, and 11. It was widely assumed that Ramanujan had found the only ones, that these 3 primes were somehow special. In 2000, Ken Ono shattered that assumption. He proved, in a paper published in the Annals of Mathematics, that partition congruences exist for every prime number greater than 3. Every single one. Ramanujan had found the first 3 examples of an infinite family. The pattern goes all the way down, and it took 80 years for anyone to see it. Ramanujan also discovered, independently, identities that had been found by the English mathematician L.J. Rogers in 1894, but had been completely ignored and forgotten. These Rogers-Ramanujan identities connect partition theory to continued fractions in a way that seemed purely abstract until the 1980s, when Rodney Baxter showed they are essential to solving the hard hexagon model in statistical mechanics, a result from pure number theory, found by a clerk in India and a forgotten English mathematician, turned out to govern how atoms arrange themselves on a lattice. The physics was hiding inside the mathematics all along. The Hardy-Ramanujan asymptotic formula for P of n, derived through the circle method, approximates the partition function with extraordinary precision. That formula, and its later exact refinement by Hans Rademacher, turns out to be mathematically equivalent to something physicists would develop decades later. But we will get there. And then there is the taxicab. The 1729 story has become a mathematical folktale, repeated so often that the real point has been sanded away. Hardy visited Ramanujan at a nursing home in Putney when Ramanujan was ill. Hardy mentioned that his taxi had been number 1729 and that it seemed a dull number. Ramanujan replied at once that it was anything but dull. It was the smallest number expressible as the sum of 2 cubes in 2 different ways. 1 cubed plus 12 cubed, 9 cubed plus 10 cubed. Littlewood's famous comment on Ramanujan's relationship with numbers was that every positive integer was one of Ramanujan's personal friends. The usual interpretation is that Ramanujan was extraordinarily quick with mental arithmetic, which is true, but misses the real story. In 2015, Ken Ono and Sarah Trabat-Leder showed that Ramanujan had not just noticed this property in the moment. He had been studying the equation a cubed plus b cubed equals c cubed plus d cubed before he ever came to England. In his notebooks, he used 1729 and the theory of elliptic curves to develop formulas related to mathematical objects called K3 surfaces, which were not even named until the 1950s, and to generate infinitely many near misses for Fermat's last theorem. What looked like a parlor trick at Putney was the visible tip of a research program that anticipated mathematics by 4 decades. The formulas Ramanujan was sending Hardy in 1913 were already entangled with mathematical objects that would not be named until the 1950s and would not be connected to physics until the 1980s. He was not ahead of his time. His time has not arrived yet. But the partnership that produced this work came at a cost that should make you angry. Because what happened to Ramanujan at Cambridge is not a rescue story. It is an account of what the machinery of empire does to the people it claims to elevate. Within months of his arrival, the First World War began. Cambridge emptied of its young mathematicians. Littlewood joined the war effort, working on artillery ballistics. The intellectual community Ramanujan had traveled halfway around the world to join largely ceased to exist. He reported that the professors had lost their interest in mathematics owing to the war. He was isolated in a way that is hard to overstate. A vegetarian Brahmin in wartime England, where food shortages made even basic provisions scarce, let alone vegetarian ones. He refused to eat in the college dining hall, fearing that his food would be contaminated by contact with meat. He cooked for himself in his rooms at odd hours with whatever he could find. A friend who visited him reported that a typical lunch was plain boiled rice with chilies and mustard fried in butter, occasionally with a piece of cucumber. Once, horrified to discover that Ovaltine contained powdered egg, he was caught in an air raid shortly afterward and became convinced it was divine retribution for having violated his dietary code. Hardy described him as fatalistic. Like all Indians, Hardy wrote in a sentence that reveals more about Hardy than about Ramanujan. He is fatalistic, and it is terribly hard to get him to take care of himself. His health declined seriously from 1917 onward. He spent time in nursing homes and sanatoria across England. Thompson's Lane Nursing Hostel in Cambridge, Mendip Hill Sanatorium near Wells, Matlock House Sanatorium in Derbyshire, Fitzroy House in London, Colonet House in Putney. The diagnoses kept shifting: tuberculosis, vitamin deficiency, blood poisoning, gastric ulcer. No treatment worked because none of them addressed the actual disease. From Matlock, he wrote a devastating letter on June 19, 1918, about the cook who scorched his food and left the rice raw, and how he had gone without dinner entirely. That letter survives. You can read it in the archives. It is the letter of a man who is starving in one of the wealthiest countries on earth while holding a fellowship at one of its greatest universities. The pattern of his illness tells its own story. He would improve slightly, begin working again with ferocious intensity, then collapse. Each recovery was shorter than the last. Each collapse deeper. Hardy visited him regularly and found him increasingly withdrawn. The mathematics never stopped. Even in the sanatoria, even when he could barely sit up, Ramanujan was working. He filled pages, the mock theta functions, the partition identities, the modular equations, all of it flowing from his pen, while his body was disintegrating around him. Janaki, in a later interview, said he did not seem to realize how sick he was. Or perhaps he did realize, and that is why he worked with such urgency. He was diagnosed with tuberculosis and severe vitamin deficiency, but the diagnosis never quite fit. Hardy noted in February 1918 that there was no coughing, no spitting, no crude lung trouble. One doctor told Hardy he suspected some obscure oriental germ trouble imperfectly studied at present. The phrase tells you everything about the state of imperial medicine. In 1994, Dr. D.A.B. Young published a detailed retrospective diagnosis in Notes and Records of the Royal Society of London. His conclusion was that Ramanujan almost certainly suffered from hepatic amoebiasis, a parasitic liver infection caused by the organism Entamoeba histolytica, contracted during earlier bouts of dysentery in Madras. Untreated amoebic infection can lie dormant for years before the parasite migrates to the liver, causing abscesses, pain, and systemic deterioration. The drug emetine, which could have cured him, was available even in 1920, but Ramanujan's English doctors were tuberculosis specialists, not tropical disease experts. They never asked about his history of dysentery. They never considered a parasitic cause. A treatable disease killed the greatest natural mathematical talent of the 20th century because his doctors did not think to ask the right questions about a patient from the wrong part of the world. And before that slow death was finished, it nearly ended faster. In late 1917 or early 1918, Ramanujan attempted suicide by throwing himself onto the tracks at a London Underground station. The train driver managed to stop. Scotland Yard arrested him. Attempted suicide was a criminal offence in England. Hardy intervened to secure his release, reportedly by emphasizing Ramanujan's status as a Fellow of the Royal Society, an honour that had just been conferred or was about to be. Young's analysis noted that chronic amoebiasis disrupts mental equilibrium and can produce severe depression, the isolation, the malnutrition, the untreated illness, and a specific bitter disappointment being passed over for election as Fellow of Trinity College in October 1917. All contributed. The honours came eventually. Fellow of the Royal Society on May 2nd, 1918. Fellow of Trinity on October 13th, 1918, the first Indian to receive that distinction. But by then, his body was broken. Here is a second misconception worth correcting. You may have heard that Ramanujan worked without proofs because he was self-taught and did not know how to construct them. This is wrong. Ramanujan could and did produce rigorous proofs when Hardy pressed him. His dissertation on highly composite numbers, which earned him a Bachelor of Arts by Research from Cambridge in March 1916, runs to 62 pages of carefully structured mathematical argument. He worked without proofs in his notebooks, not because he lacked the ability, but because the results came to him faster than formal derivation could follow. The notebooks record destinations, not journeys. And as Bruce Burnt discovered after spending over 40 years proving Ramanujan's results, many of them, when finally verified, required mathematical techniques that did not exist during Ramanujan's lifetime. He was writing down answers to questions that could not yet be formally posed. The roads to his destinations had not been built. He sailed from England on February 27, 1919, and arrived in India on March 13th. Despite his rapidly deteriorating health, he continued working from his sickbed with what can only be described as urgency. His wife Janaki later said he spent so much time on mathematics that he did not go to the temple, and that she and her mother had to feed him because he had no time to eat. The last entry in his notebook was made 3 days before his death. Srinivasa Ramanujan died on April 26, 1920, in Kumbakonam. He was 32 years old. Some of his Brahmin relatives refused to attend the funeral because he had broken the prohibition against crossing the ocean. Remember Baker and Hobson, the two Cambridge professors who returned Ramanujan's letters without comment in late 1912. Both of them signed his nomination for Fellow of the Royal Society in December 1917. They would not read his work when he was an unknown clerk. They endorsed him once Cambridge had validated him. Hans Eysenck, the psychologist, later noted the pattern bluntly. Ramanujan tried to interest the leading mathematicians of his day but failed because his work was too novel, too unfamiliar, and they simply could not be bothered. There is also a reported bureaucratic note from the Indian colonial administration, possibly apocryphal but widely cited, that captures the institutional response to his early petitions for support. What caste is he? Treat as urgent. Even urgency in a colonial system was filtered through the question of what kind of person was asking. Think about that the next time someone tells you institutions exist to identify talent. But Ramanujan's death was not the end of his mathematical output. It was the beginning of a different kind of mystery. After he died, the papers from his last year were sent to Hardy at Cambridge. Hardy apparently passed them to G.N. Watson sometime between 1934 and 1947. When Watson died in 1965, his papers were in total chaos. One account describes them covering a room floor to a depth of 1 foot, scheduled to be incinerated within days. A mathematician named J.M. Whittaker, who happened to be sorting through the mess, recognized Ramanujan's handwriting and rescued the manuscript by chance. It was sent to the Trinity College Wren Library on December 26, 1968. The catalogue entry listed it as a 139-page manuscript by S. R. Ramanujan on Q series. Nobody opened it. Nobody examined it. It sat there for 8 years. In the spring of 1976, George Andrews of Pennsylvania State University visited the Wren Library to look at Watson's papers. He found 138 pages in Ramanujan's handwriting, over 600 formulas, no proofs. More than half the material concerned mock theta functions, the very objects from the deathbed letter. Andrews described the moment afterward, the electric realization that what he held was the mathematical output of Ramanujan's final year, and nobody had understood any of it until the moment he picked it up. Bruce Berndt called it the mathematical equivalent of finding Beethoven's 10th Symphony. 56 years, the final mathematical testament of the most gifted natural mathematician of the modern era, sat in a library for 56 years because no one looked. Consider how that happened. The manuscript was not hidden, it was not classified or locked away. It was catalogued at the Wren Library under Ramanujan's own name. Dozens of mathematicians who worked on Ramanujan's earlier notebooks walked past it or could have requested it at any point. Nobody did. The mathematical community knew Ramanujan had been prolific in his final year. Hardy had mentioned it. Watson had published analysis of individual mock theta functions from the deathbed letter, but nobody thought to check whether there was more. The assumption, apparently, was that whatever Ramanujan had written in his final months was either too fragmentary to be valuable or had already been accounted for. That assumption was catastrophically wrong. The lost notebook contained more original mathematics than many full careers produce. More than 600 formulas, virtually all of them correct, many of them decades ahead of existing theory. It sat in a box on a shelf while the mathematical world slowly, painfully rediscovered fragments of what Ramanujan had already written down. The Lost Notebook was first published on December 22nd, 1987, Ramanujan's 100th birthday. Andrews and Berndt spent the next 4 decades proving its contents, publishing 5 volumes between 2005 and 2018. Watson had estimated in 1929 that understanding Ramanujan's work would take at least 5 years of hard effort. It has taken more than 40, and it is not done. Andrews has stated that mathematicians are probably several decades away from a complete understanding of the mock theta functions alone. And here is the part that should keep you up tonight. The Lost Notebook contains over 600 formulas. A significant number remain unproven. We do not know what they describe. We do not know what physics they encode. We only know that every time mathematicians have managed to prove one of Ramanujan's claims, it has turned out to be correct, and it has turned out to matter. So we need to talk about why it matters. Because the connections between Ramanujan's mathematics and fundamental physics are not metaphors. They are not loose analogies. They are exact, and they are confirmed. Start with the most famous result. Ramanujan included in his first notebook and mentioned in his first letter to Hardy, the claim that the sum of all positive integers, 1 plus 2 plus 3 plus 4, continuing forever, equals negative 1/12. He knew how this looked. He wrote to Hardy, "If I tell you this, you will at once point out to me the lunatic asylum as my goal." In the conventional sense, the series obviously diverges. The partial sums grow without bound. But Ramanujan independently developed a summation technique based on the Euler-Maclaurin formula that assigns this finite value to the series. And his result agrees precisely with the value obtained by analytic continuation of the Riemann zeta function at -1. The value -1/12 is not a trick or a misunderstanding. It is a real, rigorous mathematical result with a precise meaning. The question is what that meaning connects to. The answer is string theory. But before we get to strings, consider another result from Ramanujan's notebooks that has direct physical consequences. In 1914, Ramanujan published a paper in which he presented several extraordinary formulas for pi. One of them is so efficient, it borders on absurd. It states that 1/pi equals the square root of 8 divided by 9,801, multiplied by an infinite sum in which each successive term adds roughly 8 correct decimal places of pi. Each single term. 8 digits. Before Ramanujan, the best series for computing pi added about 1 decimal place per term. His formula was so far ahead of existing methods that nobody used it for 70 years. In 1985, William Gosper used Ramanujan's formula to calculate pi to 17 million digits, at the time a world record. The Chudnovsky brothers later modified Ramanujan's approach to create a formula that adds roughly 14 digits per term, and variants of this method underlie essentially every modern computation of pi, including the current record of over 100 trillion digits. Every time your computer calculates pi to high precision, it is using mathematics that Ramanujan developed in colonial India with a slate and chalk. And Ramanujan did not produce just one formula for pi. He produced dozens. His notebooks contain an entire garden of pi formulas, each more efficient and more mysterious than the last. Some of them have still not been fully explained. Mathematicians can verify they are correct, can prove they converge, can use them computationally, but the question of how Ramanujan found them, what insight or vision led him to these specific combinations of factorials and exponentials and constants, remains open. The formulas do not follow from any standard method. They appear to have been seen, not derived, as if Ramanujan had a window into a room where pi's digits were already written on the wall, and he was simply reporting what he saw from different angles. In bosonic string theory, the partition function of an open string is the inverse of the Dedekind eta function, raised to the 24th power. The 24 corresponds to the 24 transverse vibrational directions of a string propagating in 26 space-time dimensions, 26 total dimensions, minus 2 for the string's world sheet leaves 24. The factor that forces the number of dimensions to be exactly 26 and no other number comes from regularizing the zero-point energy of the string's harmonic oscillators. Each oscillator has a ground state energy proportional to its frequency, and the total zero-point energy involves summing the natural numbers 1 plus 2 plus 3 plus 4 onward. For Lorentz invariance to hold, for the physics to be consistent, you must assign that sum the value -1/12. Ramanujan's result, written in a notebook in Kumbakonam decades before anyone conceived of strings or extra dimensions. Terry Gannon of the University of Alberta called this one of the most remarkable formulas in science. But the string theory connection runs deeper than a single summation. The mathematical language of string theory is the theory of modular forms, and modular forms were Ramanujan's native territory. Jeffrey Harvey of the University of Chicago published a detailed analysis through the Royal Society in 2002, showing how Ramanujan's mathematics permeates the foundations of string theory. A closed string at a fixed time is a circle embedded in space. The finite temperature path integrals for strings depend on the modular group, the same symmetry group that governs the transformation properties of modular forms. When strings split and recombine, the identities that ensure the consistency of the amplitudes are identities among modular functions, the same class of functions Ramanujan was producing by the hundreds. And then the black holes. This is where the story crosses a line from remarkable to genuinely disturbing. The Hardy-Ramanujan asymptotic formula for the partition function, derived in 1918, gives an approximate value for P of n that becomes increasingly accurate as n grows large. The formula involves the exponential of pi times the square root of 2n divided by 3, divided by 4n times the square root of 3. It is elegant, it is precise, and it turns out to be mathematically equivalent to what physicists call the Cardy formula for counting microstates in two-dimensional conformal field theory. This is not a vague analogy. It is not a poetic comparison. It is the same formula, derived independently from completely different starting points. One by a clerk and a Cambridge don working on number theory in 1918. The other by physicists working on quantum gravity decades later. Why does this matter? Because of what happened in 1996. Andrew Strominger and Kamran Vafa used string theory to perform the first microscopic counting of black hole states. A black hole has entropy. Bekenstein and Hawking showed in the 1970s that a black hole's entropy is proportional to its surface area. But entropy in statistical mechanics counts microstates, the number of distinct microscopic configurations that produce the same macroscopic appearance. For a black hole, those microstates had never been counted from first principles. Strominger and Vafa managed it for a specific class of supersymmetric black holes by mapping the problem to a two-dimensional conformal field theory, where the generating function for the microstates is a modular form. The counting formula that emerged was the Hardy-Ramanujan-Rademacher formula. The exact expansion that Rademacher refined from Hardy and Ramanujan's original work reproduces the quantum gravitational corrections to black hole entropy term by term, not approximately, exactly. Tabolkar wrote that the entropy of the simplest black holes is given by counting partitions of a positive integer using integers of 24 different colors, a problem that sits squarely in the territory Ramanujan mapped a century ago. Think about what that means. In 1918, Ramanujan and Hardy were asking a simple question. How many ways can you break a number into smaller pieces? They had no concept of black holes. Black holes were not even predicted by general relativity until Schwarzschild's solution in 1916, and nobody at that time imagined they might be real physical objects with thermodynamic properties. Yet the formula they derived for counting partitions is the exact formula that counts the quantum states inside a black hole. The universe used the same mathematics for both problems. Ramanujan found it while solving one. Physics found it while solving the other. The match is exact. And the mock theta functions from the deathbed letter complete the physical picture as described earlier. The mathematics a dying man sent to Hardy 3 months before his death turned out to be the precise mathematical objects needed to count the quantum states of the most extreme gravitational objects in the universe. That is not a coincidence. That is not luck. That is something we do not have a word for. But there is more. There is also the Casimir effect. In 1948, Hendrik Casimir predicted that two uncharged conducting plates, placed very close together in a vacuum, would experience a measurable attractive force caused by quantum vacuum fluctuations. The theoretical calculation requires summing the zero-point energies of all electromagnetic modes between the plates. That sum diverges. Zeta function regularization assigns the value -1/12 to the divergent component, exactly as Ramanujan's technique does, and the result is a finite, experimentally confirmed force. The Casimir effect has been measured to high precision. The -1/12 is not abstract. It is a physical prediction. That matches experiment. Ramanujan had it in his notebook. In 1987, at Ramanujan's Centennial Conference at the University of Illinois, Freeman Dyson, one of the most versatile physicists of the 20th century, made a prediction that sounded at the time like poetry. My dream is that I will live to see the day when our young physicists, struggling to bring the predictions of superstring theory into correspondence with the facts of nature, will be led to enlarge their analytic machinery to include not only theta functions, but mock theta functions. The audience may have taken this as rhetorical flourish. It was not. Dyson understood something that most people in the room did not, that Ramanujan's mathematics was not merely beautiful, it was predictive. It was aimed at something, and the direction it was aimed in was toward physics that did not yet exist. That dream has been substantially realized. In 2015, Ken Ono, John Duncan, and Michael Griffin proved the umbral moonshine conjecture, connecting 23 instances of moonshine, a deep and still mysterious relationship between modular forms and the representation theory of finite groups, to structures that directly involve Ramanujan's original 17 mock theta functions. Moonshine itself is one of the strangest phenomena in mathematics. The name was chosen precisely because the connection between modular forms and group theory seemed so improbable, so unmotivated, that mathematicians initially suspected it was a coincidence or a joke. It was neither. John Conway and Simon Norton conjectured the connection in 1979. Borchards proved it in 1992 using vertex algebras from string theory. And at the heart of the deeper umbral generalization sit Ramanujan's mock theta functions, the objects from his deathbed letter. Ono said it is amazing that these two letters form the cornerstone of what we know about moonshine. The discoveries keep arriving, and their pace is accelerating. In 2000, Ono extended Ramanujan's partition congruences to every prime modulus greater than 3 published in the Annals of Mathematics. Around 2011, Brunier and Ono found the first exact finite algebraic formula for the partition function, something mathematicians had been searching for since Euler first studied partitions in the 18th century. In 2012, Ono, Folsom, and Rhodes proved Ramanujan's deathbed conjecture about mock theta function behavior at singular points. In 2024 and 25, Ono and collaborators published results in the Proceedings of the National Academy of Sciences showing partition functions can detect prime numbers, a connection nobody had suspected. Ono described Ramanujan's approach. He was really a poet, not a problem solver. Formula after formula, not apparent where he is going. Someone who could set down paths of beginnings of important theories without knowing why we would care as mathematicians of the future. Researchers at the Indian Institute of Science recently showed that Ramanujan's pi series, formulas he published in 1914 for computing 1 over pi at extraordinary speed, each term adding roughly 8 correct decimal digits, emerge naturally from conformal field theory. William Gosper used one of those series to compute 17 million digits of pi in 1985. The Chudnovsky brothers developed a variant adding about 14 digits per term that has been the basis for every subsequent pi computation record. Ramanujan produced these series with no known derivation. They simply appeared in his notebook. They were correct, and they connected to physics that would not be formulated for 60 years. The algebraic objects at the core of Richard Borchards' proof of monstrous moonshine, which won the Fields Medal in 1998, trace back to formulas from Ramanujan's first letter to Hardy. Pierre Deligne's proof of the Ramanujan conjecture, the bound on the tau function from Ramanujan's 1916 paper, was central to Deligne's resolution of the Weil conjectures, earning the Fields Medal in 1978. 2 Fields Medals awarded substantially for proving what a self-taught clerk conjectured or intuited. Consider what that means about the depth of his conjectures. The Fields Medal is the highest honor in mathematics, awarded every 4 years to mathematicians under the age of 40 for outstanding work. Deligne's proof of the Ramanujan conjecture required the full machinery of algebraic geometry, étale cohomology, and the resolution of the Weil conjectures, some of the deepest mathematics of the 20th century. All of it to confirm something Ramanujan had stated, without proof, in a paper in 1916. He had simply looked at the tau function, observed its behavior, and written down the bound. It took 60 years and the deepest mathematical tools ever developed to verify that he was right. That fact alone should be front-page news. It never has been. So what does this mean, and why should it unsettle you? In February 1960, the Nobel laureate Eugene Wigner published a paper titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." His observation was that mathematics developed for purely abstract reasons with no physical motivation. Turns out, again and again, to be exactly what physicists need. Complex numbers were invented to solve polynomial equations. Centuries later, they became essential to quantum mechanics. Group theory was developed as pure algebra. It became the language of particle physics. Riemannian geometry was abstract mathematics. It became the foundation of general relativity. Wigner called this a wonderful gift, which we neither understand nor deserve. He considered it deeply mysterious that the universe should be comprehensible through mathematics at all, let alone through mathematics that was developed without any reference to the physical world. Ramanujan is the most extreme case of Wigner's puzzle in the entire history of science. He is the puzzle made flesh. He did not develop mathematics for physics. He did not know physics. He was not trying to describe the natural world. He was pursuing pure mathematical beauty, guided by what he called visions from a goddess. And the structures he found turned out to be the architecture of the universe at its most fundamental level. Hardy the atheist wrote in A Mathematician's Apology in 1940, "I believe that mathematical reality lies outside us, that our function is to discover or observe it, and that the theorems which we prove and which we describe grandiloquently as our creations are simply our notes of our observations." He also wrote, 317 is a prime, not because we think so, or because our minds are shaped in one way rather than another, but because it is so, because mathematical reality is built that way. Ramanujan, the mystic, believed the goddess placed equations on his tongue. They arrived at the same conclusion from opposite ends of the philosophical spectrum. Mathematics is not something we invent. It is something we find. And Ramanujan found more of it, faster, with less apparatus than any other human being in recorded history. The standard deflection is to say he was simply a genius, extraordinary pattern recognition, a brain that worked differently. And that may be true, but it does not address the deeper problem, because there are many geniuses in the history of mathematics. Gauss was a genius, Euler was a genius, Hilbert, Noether, Grothendieck, all geniuses. None of them produced mathematics that they could not explain, that arrived through dreams, that outpaced their own ability to provide justification, and that turned out to describe physics that would not be conceived for decades. The standard genius explanation accounts for speed, for depth, for brilliance. It does not account for direction. It does not explain why Ramanujan's intuitions pointed again and again toward the specific mathematical structures that the physical universe turned out to require. A random genius working in pure mathematics might produce beautiful results that have no physical application. Many have. Ramanujan's results land on physics like arrows hitting a target that had not been set up yet. The question is not how Ramanujan's brain worked. The question is why the patterns his brain recognized turned out to describe physical reality. If mathematics were purely a product of the human mind, then being gifted at it would be like being gifted at chess. Impressive, but contained. But chess moves do not encode black hole entropy. Musical compositions do not predict the Casimir effect. The fact that Ramanujan's purely intuitive mathematical structures map onto the physical universe is not explained by saying he was talented. It is explained only if those structures were already embedded in reality and he was perceiving them. We do not have a framework for this. We do not have a theory of how a human being accesses mathematical truth directly. We have only the evidence. Notebooks full of results that took the rest of mathematics a century to catch up with. Formulas from a deathbed that describe the quantum states of black holes. A summation from a clerk's notebook that determines the number of dimensions in space-time. Partition congruences that connect to open problems in 21st century mathematics. And 600 formulas in the lost notebook, many still unproven, some not yet placed in any known theoretical framework. Ken Ono, who has done more than any living mathematician to extend Ramanujan's legacy, said that Ramanujan is not the product of an ordinary school system. He is one of those unusual minds, those names that we all know about. Think Einstein, think Newton. I want you to now think Ramanujan. George Andrews, who found the lost notebook, said he holds Ramanujan in great awe. The way he thought about mathematics is still in my mind mostly a mystery. Hardy gave Ramanujan 100 on his scale. He gave himself 25. When life wore him down, when he was forced to sit through the company of pompous and tiresome people, he consoled himself with one thought. Well, I have done one thing you could never have done, and that is to have collaborated with both Littlewood and Ramanujan on something like equal terms. He called that collaboration the one romantic incident in my life. Ramanujan died at 32. If he had lived a normal span, if his doctors had identified a treatable infection, if wartime England had been capable of feeding a vegetarian, the landscape of mathematics and possibly of physics would be unrecognizable. Hardy lived to 70 and was mathematically productive well into his 60s. Euler lived to 76 and was producing mathematics until the day he died. Gauss lived to 77. Ramanujan's output in 15 years of work, much of it done in poverty and illness, already comprises roughly 3,900 results across 3 notebooks, and the lost notebook, what would 40 more years have produced? What would he have done with the computational tools that arrived in the 1940s? What would he have made of quantum field theory, which was being developed in the years just after his death? We cannot know. But burnt who spent more time inside Ramanujan's notebooks than any person alive, said flatly that some of Ramanujan's mathematics is simply startling. If he had not discovered it, nobody ever would have. That is not hyperbole. It is a statement about the nature of his results. They do not sit on natural pathways that other mathematicians would eventually have walked. They appear to come from somewhere else entirely. We lost decades of output from a mind that operated a century ahead of the mathematics around it. We lost it because the British medical establishment in 1918 did not think to ask an Indian patient about dysentery. We lost it because wartime rationing could not accommodate a vegetarian. We lost it because the colonial system that brought him to England treated his survival as somebody else's problem. His wife Janaki was widowed at 20 with no children, her husband's Brahmin relatives having boycotted the funeral. She lived in Mumbai for 8 years, learned tailoring and English, returned to Madras, and opened a tailoring school. She received a pension from the University of Madras of 20 rupees per month. In 1950, she adopted an orphaned boy. After the lost notebook was discovered, she lamented that no statue of her husband had ever been made. Professor Richard Askey organized 100 mathematicians to commission a bronze bust. It was presented to her at the University of Madras in 1985, 65 years after Ramanujan's death. The notebooks are in libraries in Cambridge and Madras. They contain formulas proven correct in the 80s, the 2000s, 2025, and formulas not yet proven. Nobody knows what those remaining formulas describe. Nobody knows what branch of physics they address. Nobody knows if the science they require has been invented yet. We only know the pattern. Every time we have caught up to Ramanujan, he has been right. Every time we have placed his work in a physical context, it has described something real. Every time mathematicians have said they were close to finishing the work of verification, they have discovered another layer beneath the one they thought was the bottom. Freeman Dyson called Ramanujan's legacy a garden. It is a garden that keeps growing. New flowers appear in soil that was turned over a century ago, and we are still behind the man who planted it. A clerk in Madras, earning £20 a year, who failed his university exams and nearly starved on the streets of his own country before writing letters to professors who would not read them, who crossed an ocean he believed was forbidden, who starved, again, this time in England, who tried to die on the tracks of the London Underground, who was diagnosed with the wrong disease and treated with the wrong medicine, who filled notebooks until 3 days before his death, who said a goddess wrote equations on his tongue. We have no explanation for him. We have only his work, and his work describes the universe.